right, we're starting section P.2, which is going to be primarily on exponents, the law of exponents that we refer to them as, and on scientific notation. So we'll kind of go through multiple ones, give examples, and then kind of culminate it and put it all together. So we're going to look at our first law of exponent. I'm going to see if I have b to the fifth, and I want to times that by b cubed. From before, in section P.1, we were looking at what does that mean. That means that for b to the fifth, that I'm taking b and I'm multiplying it by itself 5 times. Whoops. And then for b cubed, I have to multiply it by itself 3 times. So I'm multiplying these and these all together. Well, notice that's kind of just awkward just to write it all out like that. It would be very nice if we can condense it down. So how many b's do we have multiplied all together here? Well, if you count them up, or look there, we have 8 of them. So I can rewrite this as b to the 8th. Hence, that gives me my first law of exponent as b to the m times b to the n. I'm going to refer to that as, what did we do with the 5 and 3 that I originated to get 8? We added. So this is the law of exponent means I'm going to take the m plus the n to get our answers, okay? It's referred to kind of as the product rule. When multiplying exponential expressions with the same base, then we're going to add our exponents. So sometimes I refer to this as 2 bases and 2 powers. When they're the same, we're going to add them together. So therefore, if I look here, I have 5 and 5 bases are the same, so I'm going to add the exponents together. So I keep the 5 the same. This 5 stays the same. It does not change. The only thing that changes is the sum of the exponents. So 5 to the 11th would be my answer. Same way here, 4 and 4, 2 bases that are the same. So I'm going to end with the same base, but I'm going to add these exponents. Well, negative 3 plus 10. Or 10 minus 3, you can think of it as, is 4 to the 7th. Now, when I look at something like this that has 2 things together, multiplied ultimately, we want to make sure that we are doing things separately. So when I say that, when I look at these, what we call monomials, we're going to look at the numbers first, then we're going to look at the x's, then we're going to look at the y's. So I can change them around by our properties. If you remember the commutative property and the associative property, I can do all of that, but I'm not going to waste time or space to do that. Basically, we want to multiply the 5 times the 2 and give me a 10. Then I want to return to my x's. I have 3 x's there, 7 x's there, 2 bases with 2 powers. That means I can add those exponents and get a 10. And likewise, I have a y to the 5th and y cubed. So I have 5 y's here, 3 y's here. All together, we have 8 y's. So if you do it in pieces, it just makes it so much easier just to work itself out. Now again, start here and do the outside numbers. We're multiplying all these straight through. That gives me a negative 35, and if I look at my a's, I have 4 a's in the front, 3 a's in the back, all together by my law of exponent. I would add those exponents. Now, the question would be, on this first b, what's the exponent? I don't see anything, but sometimes when we don't see anything, we think they're zeros, but this is actually a 1. That means I have 1 b there. We just don't write the 1. But I do have 4 b's back here. So I have 1 b here, 4 b's here. So all together we would have 5 b's. And so negative 35, a to the 7th, b to the 5th would be my final answer there. Okay? Now, what happens if I have bases that are the same that I am dividing? So for instance, if I end up having, say, use that b to the 5th and b cubed again, b to the 5th, and I'm dividing by b cubed this time. Well, what does it mean? That exponent means I'm multiplying b by itself 5 times. Remember, it's not, it's not 5 times b. It is b times b times b, okay? All right, so I need another b there. Change my width or my thickness back. Divide that all by b times b times b. Now, when we're dividing 2 things that are the same, like 5 over 5 or 10 over 10, we basically say they cancel each other out or they're 1. So by products here, if I have things that are the same on top and bottom, I can cancel those out. Now look what you have left. You have 2 b's that are on the top. That's very important. That gives me a b to the second if I want to rewrite that in simplified version. So the question would be, what do I do to this 5 and 3 over here to get the 2 in the final exponent? Well, I'm hoping you tell me you subtract 5 minus 3 to get 2. And that's exactly what our law of exponent is going to tell us. When you have bases that are the same that you are dividing, now we end up subtracting those exponents to get the new answer for that. And that's referred to as the quotient rule. When dividing exponential expressions with the same non-zero base, then we are going to subtract the exponents to get the leftover, basically. Now again, the base doesn't change, so here I have a negative 3. I'm still going to end with a negative 3, but now I'm going to take the 9 minus the 6, which gives me a 3. Now, you could actually write that out as negative 27 because that's what negative 3 times negative 3 times negative 3 is, but you can leave it in exponential form. Here, my base is pi, so I'm going to end with a pi as the base, but I'm going to subtract this 5, and don't forget, there's an invisible 1 there. 5 minus 1 gives me a 4, and that's the best I can write that in exact form. Now these two examples we turn to just like we were doing up here, where we did our numbers together, then we did our x's, then we did our y's, and same for a's and b's over there. So I'm going to do 32 divided by 4. So if I do like a canceling type thing, 4 goes into 32 8 times. Technically this should be a 1, but that's not going to do anything to my answer. I have 2 x's down here, 10 x's on top, so I'm going to cancel 2 of them out, and I leave how many? Well, we leave 8 in the top, and 10 down here, we'll cancel 10 up here, leaving 2 in the top. So again, subtracting 12 minus 10 to give me a 2. Therefore, 8x to the 8, y to the second would be my final answer. Next example, negative 7 into 49. Well, if we divide those, that's what this fraction bar means to do. 49 divided by negative 7 would leave me a negative 7. Again, I have 1a in the bottom, 6a in top. 1a is going to cancel with 6 up here, with 1 up there, leaving 5 in the top. And 3 are going to cancel with 3 of these 5, leaving me 2. Again, subtracting 5 minus 3. Therefore, negative 7a to the 5th, b squared, or b to the second, is going to be my final answer there. Okay? All right, very good. These kind of go pretty fast. Hopefully you remember them from Algebra 1, these rules. Now, we're going to continue with a special case of the quotient rule. And I just said earlier that if I wanted a value of 1, that could be found by taking 5 over 5, 10 over 10. That gives me 1. Okay? I'm going to do that same idea, but use a different expression. Instead of a number, I'm going to use variables. So I'm going to say b to the 5th all over b to the 5th. I'm hoping that you see that that is the same thing. Just like this 5 over 5, b to the 5th over b to the 5th is the same exact thing. So I could say that that is equal to 1. Now, by using our quotient rule, which says if I have bases that are the same, we can subtract these exponents. I can mathematically prove that this is true, just by that second law of exponents. And so, if I do the subtraction, then I get b to the 0. So what I've just proven is our next kind of rule that I have for you. It's called the zero exponent rule. And if b is any real number other than 0, then b to the 0 is always equal to 1. Now I have a lot of students that like to give me 0 on that. Remember, anything to the 0 exponent is 1. It's not 0, it's 1. So here I have negative 2 to the 0 power. Oh, I see that 0 power. I know all of that is 1. Pi to the 0 power. Anything to the 0 power is 1. Now be careful here on this. There's no parentheses around this negative 2. So it's kind of like I'm looking at just 2 to the 0 and then I have a negative out front. Now 2 to the 0, that all is 1, but this is a negative 1 as my final answer. Here I have everything to the 0 power. Anything to the 0 power is 1. But this example now only has a 0 on the y. There's no parentheses here. So just this piece right here is 1 that I'm timesing by that number out front. So technically this answer is going to be a 10. Now I have all this big expression here with big powers and all that kind of stuff, but ultimately look what the power is on the outside. So I have no care in the world about what's inside here. All I know is that it's something to the 0 power, which reduces to 1. Okay, so you may want to make sure that you star this one. This is one that kids kind of forget when I've taught exponents before. Okay, all right, let's move forward. Moving on to negative exponents, and this kind of gets us into the idea of what we've already seen, b to the 5th over b to the 3rd, but I'm actually going to reverse those now. So, again, by definition, what is that top? It's b times b times b. On the bottom, it's b times b times b times b times b, and because I can cancel those now, this time the leftover is in the denominator. So I can write that as b squared, but you want to be cautious because you just don't want to leave the top blank. The top has to be something, and that something is going to be a 1. So I can prove to you that is equal, but I can also look at b to the 3rd over b to the 5th, and what did we say? By our law of exponent, if I have two bases that are the same, I can subtract those exponents when dividing. So if I do b to the 3 minus 5, this gives me a b to the, well, 3 minus 5 is a negative 2. Hence, looking at it two ways, I have this and I have this, means that these two things are equal. Hence, this is our negative exponent rule. Okay, basically, you can move things over the division of the fraction. It's kind of the layman's terms of it. So if we have b to be any real number other than 0 and n is a natural number, remember that's those counting numbers, then b to the n is equivalent to 1 over b to the n. So we can flip it over the fraction bar and make it positive. Basically, if you have a negative exponent, the expression is allowed to flip to the other side. And I've had good success of kids thinking of it that way, or students thinking of it that way. Not all of us are kids here. All right, so basically if you have, okay, so if we look at 3 to the minus 2. 3 to the minus 2, this is my n, here's my base. So it's in the top originally, because I could put that over 1 if I wanted to. I'm going to flip that to the bottom and make the exponent positive. So this equates to 1 over 3 squared. Now, 3 squared is not too bad. I could go ahead and figure that out as 9, because that's 3 times 3. If I look at this guy, I'm going to take this base, flip it to the bottom, and make that exponent positive. So we're going to have 1 over negative 3 to the 4th. Now again, negative 3 to the 4th is not too bad. You can multiply it out 4 times. If we get something really large, we probably won't. But this one's not too bad to give us 1 over 81 as a final answer. Now the third example has the negative exponent in the denominator. So that's why I refer to as flipping to the other side. That means I'm going to move this to the top and I'm going to make it positive. So when I move it to the top, now it becomes 5 to the 3rd power. Don't forget to make it positive. And I get an answer of 125 when I multiply 5 times 5 times 5. And now that's the last of the one terms. So we now have to go to the multiple terms. But don't panic, because again, take it in pieces. So I always think of this as over 1 to begin with. And I go piece by piece and ask myself, does this one move because it has a negative exponent? Well, if I look at the number 5, 5 doesn't have a power on it. Again, it's invisible, so it is understood to be a 1. That is not positive, or that is not negative. It is positive, so I'm allowed to keep it where it is. This x to the minus 5 now has a negative exponent, which allows us to flip it to the bottom and become positive. So I get an x to the positive 5. And if I look at y to the 6th, it's not a negative exponent, therefore it has to stay put. And my final answer, nothing can go away. I don't have multiple x's or y's that I can cancel, so that is going to be my last answer, or my final answer. Now, here we come to one that has multiple things going on. So I have an 18 and a 2 that I can cancel and leave me a 9 in the top. But now I have all these negative exponents that I'm going to have to move to the other side. Notice this one, though, is positive, so it's going to stay put. So I always just like to draw a fraction bar and go, again, piece by piece and ask myself, does this guy move or stay? It's negative, so it has to move and become positive. Does this guy move or stay? It's negative, so it has to come to the bottom and become positive. Now, we already worried about the 2, got rid of that. Now I look here and I have x to the negative 5. It's negative, so it has the right to move to the top and become positive. And if I look at this guy, it is positive. So if it's positive, you can't move it anywhere. It has to stay in the bottom. Okay, now we do have a little bit of stuff to clean up here. We do have some x's that we can cancel out, and we do have some y's that can cancel out. So if I look at this, okay, there we go. All right, so this, I've got 2 down here, 5 up here, leaves me with 3 on the top. And these, I just need to put them together. I've got 3 here and 5 here. Altogether, I have 8. Therefore, my final answer, don't forget your 9, has to be on the top, gives me a 9x cubed all over. Adding these exponents by the first law of exponent gives me an 8. And that would be your final answer. Okay? All right. Moving on down to what we call the power rule. We are going to be looking at multiple powers with one base. So I'm going to say I have b squared that I want to cube. Now, by that power of 3 on the outside, it tells me that I have to multiply what's inside here by itself 3 times. So that means to take a b squared times a b squared times a b squared. Now, this refers back to my law of exponent number 1, where I have bases that are the same that are being multiplied together. We can add our exponents. So 2 plus 2 plus 2 is a 6. Now, the question is, how do I get 6 from 2 and 3? Well, I'm hoping you tell me that you multiply those powers together, and that is exactly what we need to do. When an exponential expression is raised to a power, we are going to multiply the exponents together. Hence, here comes our new rule. If I end up having b to the m raised to the n, 1 base to 2 powers, that's when we multiply those exponents to give me b to the mn. Okay? So, let's look at these 3 examples. And again, we're going to kind of put them all together here in just a minute. But real basic, if I have a base to 2 powers, the base stays the same, and I multiply those exponents to give me a 6. Base stays the same. Multiply the 2 powers back to back with that base to give me a minus 21. Now I could go further if I said no negative exponents. Remember what we just did at the top of this page. That would actually be 1 over x to the positive 21 by flipping that over. Now, last one here, 1 base to 2 powers. Multiply those powers, keep the base the same. A to the negative 5 times negative 3 is a positive 15. And that would be our answer. So, again, the big rules are here in boxes, so make sure that you remember them and work with them. All right, now, what if I have multiple terms all to a power? So, for example, I have 3x cubed, okay? By the outside exponent, that means that I have to do 3x times 3x times 3x. So this kind of goes back to what we did previously. I could, again, do my order or do my properties and change things around, move my numbers together, redo the parentheses. But technically, what I need to do is multiply this 3, that 3, and that 3, which gives me 27. And then I need an x times x times x, which means I can rewrite that as x cubed when I add those powers together, 1 plus 1 plus 1. Now, each term here gets a power. If we compare this to this, the 3 got a power of 3, and the x got a power of 3. So hence gives me that 27x to the third. So the products to powers and quotients to powers, I'm putting them all together basically. When a product or a quotient is raised to a power, each factor must be raised to that power. So if I have A, B inside here, or if I have 10 things inside there, all to the n power, that means I have to take A to the n power and B to the n power. Again, it's not multiplying A times B, it is A to the n power, B to the n power. Likewise, if I have A over B to the n power, that means that I have to give A a power of n to be A to the n, and B a power of n, which gives me B to the n. Okay, so we have to be fair to all of them and give each one a power of n. All right, so let's look at these three examples. These three examples will help me deal with this expression here, or this rule here. So that means I have to bring the power of 3 in here, and in here. So I'm going to write it out for the first time, but you probably will get to the point where you don't have to rewrite this step. All right, so I need to take -5 to the third power. -5 times -5 times -5 means that's -125. A base to 2 powers, which is just what we did up here previously as our power rule, means I have to multiply these two together, which gives me x to the 6th. And likewise, again, I have an invisible 1 here. 1 base to 2 powers, we're also going to multiply to give us y cubed. And that's the final answer there for that one. Outside power of 3 means I have to bring that inside to each one of those. Now, that negative out front can get kind of tricky. You want to take that negative either to the top or the bottom. Doesn't matter, but you don't want to give it to both. So I'm going to treat this negative up here and kind of get rid of it out front. I'm going to do it as the -3, which means, again, I have to take that to the third power, and I also have to take this x squared to the third power. So that means I have 3x squareds in the bottom, meaning I have 2, 2, and 2 gives me a total of 6. So x to the 6th. And then -3 times -3 times -3, 3 negatives makes a negative, and 3 times 3 times 3 is 27. Nothing that you can simplify here, so that would be your final answer. And our last one, we have multiple things going on here, but the important part to remember is that every single term inside there gets a power of 2. So I have 2 squared, I have x to the 5th squared, I have y squared, and I have to, don't forget about the 7, I have to square the 7 as well. Now it's very nice, 2 times 2 here. Take this number, multiply itself this number of times, gives me a 4. Then a base to 2 powers means I have to multiply, so we're going to go x to the 10th and y to the multiply here 4th. On the bottom, it's not 7 times 2, it's 7 times 7, which gives me a 49. Now, if there was something here with the 4 and 49 that we could cancel, we would definitely do that to simplify it down, but here there is not. So we are complete with our answer for that problem. Okay, so always make sure that things are simplified. Hence, I've kind of wanted to review here at the bottom of this, simplifying exponential expressions. This is what you want to make sure that you refer to so that you know that you are completely simplified. Or I guess I should say no parentheses appear. Okay, so let's make that plural. No parentheses appear. So get rid of those. Each base occurs only once. So if you have things that can cancel, please do so, or put together, please do so. No powers are raised to powers. So again, the power rule tells us we can multiply those exponents. So you have to get rid of those. And no negative exponents or 0 exponent. So all of these conditions have to be met in order for your expression to be simplified. So make sure that you adhere to those. All right. We're almost done. We are on the last page for section 2. And we're going to kind of put it all together here with these values. And so here is one where we have an outside exponent, which means I have to bring it into every single term. So that means I have a 3 cubed. I need an a cubed. I need a b to the 6th cubed. And I need a c that's cubed. So when I have 3 cubed, that's 3 times 3 times 3, which is 27. 1 base to 2 powers, I multiply a to the 9th. 1 base to 2 powers, I multiply 6 and 3 to give me 18. And my invisible 1 multiplied with 3 gives me a c cubed. Again, if you are used to exponents and stuff, you can miss this middle step and go directly to here. Okay? Now, the next one, I am going to kind of do that as well to save us a little bit of time. But we're going to do the outside exponent first. And we will take that 2 on the inside to that negative 2. So think about, what is negative 2 squared? Negative 2 times negative 2 is a 4. And when I have a base to 2 powers, that's where we multiply. So you can write it all out like we did over here, but I'm going to go directly to x to the 6th and y to the 4th. A lot of times, I will end up multiplying or writing things out so that you see it. But then a lot of times in math, once we get the hang of it and the pattern, we miss that step. We kind of hide that and do it in our head. So then there's nothing here on an outside exponent, so I'm just going to rewrite that. And now this goes back to kind of our very first part where we're multiplying the numbers, putting the x's together, putting the y's together. So I multiply 4 and 3 to get a 12. 6x's here, 1x here gives me a total of 7. This is where we add the exponents. 4y's and 2y's here gives me 6 all together. Okay? Now, our last thing here, we have 2 division problems. So just kind of basically canceling that gives me a negative 5 I'm going to write when I do 15 divided by negative 3. Notice we have a's and b's to combine. And c, let's turn to c. c is c to the 0. That's the easy one. Remember, that goes away. That gives us a 1. So basically when we're multiplying, it goes away. But I have a to the 3rd over a to the 7th. 3 a's in top, 7 a's in bottom. That means that I'm going to have some left over in the bottom this time. I have 4 left over when I subtract those. But when I have 10 b's on top, 2 b's on bottom, I'm going to have 8 that are left over in the top. So our final answer here, we again disregard that 1, is going to be negative 5b to the 8th all over a to the 4th, and that's our final answer. Last problem on our exponents. Notice that we have a division problem in the inside to an outside exponent. Now, over on this problem, I told you to do that outside exponent first, but inside here, there are things we can simplify, and I'm going to recommend that you do that first. So I'm going to go ahead and simplify my numbers again, kind of do the 10 and the negative 30, divide those, gives me a negative 3. Notice that I have 2 m's on top, 11 m's on bottom. There is some leftover that's going to cancel. Subtracting those, and the leftover this time is in the denominator. And then notice here we have a negative exponent that, remember, negative exponents have the right to flip. So we're going to flip that to the bottom and make it positive. So I'm going to end up having another n squared here that I can actually combine with that n to the 8th. So let's recap. I'm going to have this negative 3 on top. On the bottom, I have an m to the 9th from my leftover on the m's. And when I combine these, after flipping that negative 2 to the bottom, making it positive, I have 10 in the bottom, making that an n to the 10th. Now, all of that is what's now taken to that outside exponent of 2. So it's much easier to do the simplifying first if you can, and then do the outside exponent, because now all I have to do is give that power of 2 on the inside to each one of these. And so, negative 3 squared. That's not negative 3 times 2. It's negative 3 times negative 3, which gives me a positive 9. All over 1 base to 2 powers is when we multiply by our power rule. That gives me an m to the 18th. And multiplying 10 and 2 gives me an n to the 20th. And that is our final answer for our exponents. So, doing it in pieces, and then here culminating at the end, doing a lot of it together, which is important to learn the different concepts. All right, moving into scientific notation, which also uses exponents. This is somewhat, useful in science a lot. In math, we don't do as much with it as if you probably end up doing something with science in it. So let's move this up here. All right, so scientific notation is a way to write really large numbers or very small numbers in a manageable way. Here is the rule. A number is written in scientific notation when it is expressed in the form of a times 10 to the n power, where our a value is between 1 and 10. I'm going to put the absolute value of that. So the positive version is between 1 and 10. Now notice we're including 1 but not including 10. So if I do interval notation, it would end up being something that looks like this. And n is an integer. So if we go back to section 1, you should hopefully recall that those are all the positive and negative whole numbers. Now, because the number is multiplied by a power of 10, then the decimal is moved left or right. So that's kind of the layman terms when you're multiplying by powers of 10. For a positive n, move the decimal that number of places to the right. That means I'm multiplying by 10 to the 5th power, which means it gets really big. In order for a number to get big, we're going to move our decimal to the right. If our a is negative, then we're going to move our decimal that many places to the left, which would create the very, very small numbers. All right, so if I have this number, we're going to write it into basically decimal notation, or sometimes people call it standard notation. So I have a power of 5. It is positive. We're going to get a bigger number, so I need to worry about taking this decimal 5 places to the right. So 2 to get past the 2, 3, 4, 5. These are placeholders basically for zeros. So I'm going to write the 9, 3, 2, and I have 1, 2, 3 placeholders for zeros. And if I wanted to throw a comma in there, then this would give me the standard number. Again, a different way to write it. Notice here I have negative 8.6 times 10 to the minus 4. The negative 4 means I move my decimal to the left. I'm going to end up with a smaller number. Now, ultimately, it's going to be negative. But we're going to take this decimal, move it 1 place, 2, 3, 4. That's where my new decimal is going to occur. And back over here, the decimal is back here at the end, but we don't write it if it's at the end. So I have a point, and then 1, 2, 3 zeros again, 8, 6, and normally we like to have that 0 in front just so that we have it. So here's the standard number of that, and you've probably done that somewhere in science before. Now, let's go backwards. Here, I want to take this large number and write it into something as a number between 1 and 10. Times 10 to some power. Now this is a very large number, so that means that my power is going to be positive here. Now I need to move to where I get a number between 1 and 10. Well, if I move my decimal here, that's still a big number. So we're going to keep moving until right behind the very first digit, which is right here. And so if I move the decimal there, that means I can write 6.4. Now, no need to write the rest of those zeros because that's what we're exchanging. 4 times 10 to what power? Well, our decimal's at the end to originate. If we move it back 1, 2, 3, 4, 5, 6, 7 places, that means this power has to be 10 to the 7th. Also, the next one is a very large number, so we're going to have a positive power, but it's negative. Now notice, where's the very first digit? It's 3. We're going to move our decimal to here. So I'm going to kind of do it in pieces here. Here's 3, here's 6, here's 9, and here's 12 actually. So it's going to be times 10 to the 12th. Again, it's a positive 12 because we're a very large number. And then we're going to write everything that is not a 0 in front as negative 3.21. And that will be my number between 1 and 10, an absolute value, and our power times 10 to the 12th. Turning to a small number, we're going to move, again, that decimal behind the first digit that's not 0. So we're going to move it 1, 2, 3 places. So I end up getting a 3.5. Now again, none of those other zeros can go in front or behind, but we're going to go times 10 to what power? Well, this is a smaller number, so it's going to be a negative exponent, and we went 1, 2, 3 places to the left. Therefore, this is going to be a negative 3 power. 3.5 times 10 to the negative 3 would be my scientific notated number. And our last one, to go backwards again, we're going to take this decimal and put it all the way back here behind this first non-zero number. So I'm going to keep the negative, and it's going to go 7.96 will be that number. Again, don't write these zeros in front, but we're going to exchange those for times 10 to what power? Well, here we go. 1, 2, 3, 4, 5, 6, 7, 8. And it is to a very small number, so that has to be a negative power as a negative 8. And that would be our scientific notation. Okay? Now, where does this come into play when we work with law of exponents? It's because when I have problems that look like this, now I can combine those powers of 10. So, we're going to operate with these numbers, and we might be able to use some law of exponents. Let's take a look. Perform the computations and then write our answer in scientific notation. So we want to double check that. Now, what I want to do is multiply this times this. All the numbers out front we multiply together. If you do that, you get the number 6.5, which is very nice because that's a number between 1 and 10. So now when I go to combine my powers of 10, I have 7 tens there, 8 tens there. This is one of those first law of exponents where I add those exponents and get a 15. Now, we knew 6.5 was between 1 and 10. I've combined it all into 110 here, and we should be good. Now, when I go over to this one and I combine 8.2 and I times it by 4.6, then I end up getting 37.72. Now, that number is definitely not between 1 and 10, so we're going to have to figure something out here. Now, if I go ahead and combine my exponents, 8 and 4 gives me a total of 12. Now, if you envision this, sometimes this is hard to, do I make it a 13 or do I make it an 11 when I need to move this decimal over one place to get my number between 1 and 10? I always like to think of this as, okay, this is a number that's really, really, really big. I'm going to take this decimal and I'm going to move it 12 places back here to get my really long number like this one up here, okay? But I need to now write it in scientific notation. Now, if you want to write it out with what would be 10 zeros, move this over 1, 2, and then add 10 zeros to get the 12, you can. But if you vision that with the 10 zeros, if I need to come back and bring it into here, that means I'm going to have to come back not only these 12 spaces, but then one more. So that means I need to actually make it a 13. So I'm adding 1 to that, and sometimes that's hard. I could go mathematically into that, but I like to think of it as looking at the number as a standard decimal number and then making it back into scientific notation. So hopefully that's a little bit easier for you as well. All right. So our last two problems deal with division. Again, you want to divide the two numbers that are here, and now when we're dividing these exponents, we need to subtract those. Now, we can have powers that are negative with scientific notation, so if we subtract them and get a negative number, it's okay. So I'm going to divide the 6.9 by 3, and if you do that, you get a 2.3. And when I subtract these exponents, 8 minus 10, do the top minus bottom, I get times 10 to the minus 2. Now, that's simplified. The question is it in scientific notation? Well, our power is okay, even though it's negative. This number is between 1 and 10, therefore, yes, this is my scientific notated number. And our last one gets me to where I divide these two numbers. And unfortunately, it's like the one above it, where it's not a number between 1 and 10, but if I subtract 4 minus a negative 2, 4 minus a negative 2, I get a positive 6 because this becomes a plus, which gives me a 6. Now, you can also think about flipping this one up and making it positive as a 10 squared. And again, that gives you your 10 to the 6th power. Now, let's think about this. So, a little bit more room here, maybe I could write it out. You're going to move this decimal 6 places to the right to get a standard number. So if I do that, that's going to give me 1 place past the 6, and I need 5 zeros. So here's my 5 zeros. Now, from here, my decimal is at this point. I need to bring it back to just after the 6th. So instead of going 6 places, now I need to come back 5. So in order to leave your answer in scientific notation, I need 6, and you could do 0.0, but it's not necessary, times 10 to the 5th power It's kind of backwards. When you move it to the right one time here, you've got to subtract 1 to get this power. When you move it to the left here, you've got to add a power to make it all work out. So again, that gets confusing on the adding and subtracting when you have to do that. I think it's much easier to do the standard number than come back to scientific notation. So that is our conclusion of section 2 on exponents and scientific notation. Hopefully through the practice you'll get more confident and master these concepts.